Hello everyone. In the next 15 minutes, I'm going to condense 2 years of a Marie Curie fellowship ended in July, so bear with me. The title is a mouthful, using deep reinforcement learning to coordinate multimodal journey planning with limited transportation capacity. I am Lara Kodeka, and this work has been done with Professor Vinica Hill at Trinity College Dublin. Do you remember a life before COVID, where large-scale social events were actually still a thing? The traffic congestion before, during, and at the end of them was always creating issues for everyone. We decided to study that specific trip planning problem where there is limited capacity and a lot of constraints. Given the huge step forward with deep reinforcement learning, we decided to try and see if it's possible to apply it to our complex problem. Machine learning is used a lot in transportation, but reinforcement learning is relatively a new application. To see if it's feasible, we put together a learning and evaluation infrastructure that would allow us to generate a lot of different scenarios and see how the agents would behave and learn. 2 words on reinforcement learning. The idea is to learn a policy while exploring an environment through trial and error. The policy is just the how-to for the agents to reach their goal. So, the agent is going to explore the environment by performing actions based on the current state and observing the outcome. The environment knows the state of the system and rewards or punishes the actions based on the current and future outcomes. Future rewards plays a crucial role in planning to avoid falling the local optimum issue. In our specific case, we have the agents that are the travelers. Their goal is to reach the destination just in time. No one wants to arrive too early or too late to a concert. The environment is modeled with Sumo and holds the transportation infrastructure and the traffic situation. The actions available to the agents can be divided in wait or start the journey with the selected mode of transport. The rewards are computed based on the overall goals achieved. Until now, I have not mentioned the crucial part of our study, and that's the coordination piece. We know that if you don't have enough resources and everyone has already the same arrival time, some sort of coordination is in order. There are multiple taxonomies to define coordination, but we can narrow it down with active is when the agents are talking to each other to create a plan, and there you have an exponential overhead. Passive is the one we focus on, and it's easily explained as the competition for resources. What we focused in our experiment is checking between implicit, where the agents are just observing the environment and the impact of their actions, or explicit, where we can change the reward model to punish every agent if someone would come late to the event. This can be directly translated in the multi-agent reinforcement learning paradigm, just by properly crafting the states and action spaces and varying the reward. The infrastructure that we built is based on open source projects. Ray is the distributed orchestrator that makes scalability possible by deploying the learning and evaluation in the cloud. RLlib is the deep reinforcement learning library that is based on Ray. I bet that you all know Sumo by now. And our contribution are RLlib Sumo Utils, that is the general purpose connector between RLlib and Sumo, and Persuasive, the entire set of environments, states, agents, and reward models that are presented here. All our contributions are openly available on GitHub. In the paper, we presented in depth why we choose the Proximal Policy Optimizator, PPO, learning algorithm provided by RLlib. Just to keep in mind that RLlib already implements plenty of algorithms and they are easily plugged in and just used. We created a handmade scenario that would allow us to deal with all the transportation capacity issue and in a controlled environment. We then created a naive baseline to compare all our policy against something, and the solution simulates a person checking their phone to decide their plan based on the current traffic situation and the modes proposed by Google Maps. We created a synthetic background mobility using Saga, that is an activity-based mobility generator available in Sumo contributed tools. We then run all the baseline for the different reward models, and we use those to decide how to proceed with the study. The ablation study focused on removing transportation modes and limiting the actions to make sure we could manipulate the learning and that the environment is effectively explored. We then changed the meaning of some actions, enforcing parking requirements and adding uncertainty. Finally, we introduced hard constraints such as the ownership of a vehicle as a way to impose limitations. Some details on the learning environment. We are using 1,000 agents to compete in the environment. We use different strategies for the agent start time. The start time is when we insert the agent in the learning environment, while the departure time is when the agent decides to start the journey. All the agents have a random origin within the map boundaries. The number of actions available to the agent is linear with the number of modes available. Wait is always a possible action in all the experiments. The three reward models are increasingly complex. Simple, as the name implies, divide the arrival time in too early, on time, too late, where too late is worse than too early. Observed travel time builds upon simple but keeps into account measured travel time. And observed travel time with coordination builds upon OTT and actively punishes each agent if other agents arrive too late. Concerning the aircraft mobility scenario, we built it using the random grid option in Sumo, and we selected the central location marking blue as destination. The network contains sidewalks and traffic light. We then added 2 metro lines, 3 bus routes, and we scattered parking areas all over the map. The background mobility was built with Saga, provided 20K people moving around from 5 a.m. to 11 p.m. We then varied the exact feature in the environment based on the specific experiment that we intended to run. The metric we use to evaluate the experiments are the departure time, because it tells us if the agent has learned to wait and avoid departing too early. The observed travel time, because it's the active part of 2/3 of the reward models. The waiting time at destination, because our main goal is just-in-time arrival. And the late arrival, because it was the main metric for punishment and coordination. Finally, we use the mode choice distribution to understand the policy and figure out how realistic they would actually be. Among all the experiments we run, I want to highlight some results. First and foremost, the learned policy outperformed or at least matched the naive solution all the time. Additionally, we have not found significant difference during learning in the experiment with and without background traffic, making it possible for us to focus on the one without it and speed up the experiment. We didn't find a way to make public transportation appealing enough to win over bicycle and motorbikes yet. Nonetheless, the experiment concerning uncertainty with parking requirements and the one with hard constraint represented by vehicles ownership worked as intended. Finally, I want to bring the attention to coordination and the reward models. We have not found a definitive answer concerning the impact of coordination because the results change depending on the experiment at hand. It's worth noticing that even the simple reward model brought good results, making me question how much it's worth to have incredibly complicated reward models that makes harder to understand and validate the learned policies. So, in conclusion, we show that it is possible to use multi-agent deep reinforcement learning to study the problem of coordinated multimodal trip planning with limited transportation capacity, and that through a simulated environment such as Sumo, it is possible to discover relevant features and learn viable plans. The future work goes in two directions: scalability and complexity. We intend to use our infrastructure with most scenarios and use the Monaco Stadium as the target venue for the event. And we already started working on user preferences that opened a Pandora box of trade-offs concerning sub-constraints. Anyway, thank you for your time. Here you can see the links to the full project, RLE Sumo utils, and in case you're interested, you have access to all the additional results. Thank you again for your time.